Our last video examined the building blocks of a group, and without rigorous proof, we saw the beauty of abstract algebra as we demonstrated the group of reflections and rotations of an equilateral triangle, commonly called D6. In this video, we hope to provide you with a general understanding of the order of the group and the order of each of the elements contained therein. Remember, using an infinite set of integers, we see the operation of addition takes two of these elements and maps them to another element. This is a closed binary operation. If we pick a subset of integers, such as 0 through 11, we can use the familiar example of a clock and can create a group with a finite number of elements. It is a group because it holds four properties. Closure. We can combine any two elements together and the answer is still one of the elements. Associativity. We can perform the operation on our elements by grouping them in different ways, and the final answer does not change. Identity element. There must be an element in our group that leaves the other elements unchanged. Finally, the inverse elements. All of the elements have an inverse element, and the answer when combining an element with its inverse was the identity. We then selected only three elements and placed them on a clock face. Instead of using them as numbers, we used them as vertices for a geometry, in this case an equilateral triangle. And with that triangle, we discussed the motions of symmetry. Because we can select an infinite number of integers to create our clock face, there are an infinite number of these groups. We call these groups the additive groups of integers. And for our example, the number of elements was 12. This is usually written z over z12. So let's explore some of the interesting things about the groups using our example, the additive group of integers modulo 12. First, there is something we call the order of the group. That is simply the cardinality or number of elements we have in the group. Since by definition we selected 12 to get this group, we see that the order of our group is 12. We also see we can add the element 1 to itself and get the element 2. Taking that answer, we can add that element successfully and get 3. We then continue this process very similar to raising an element to a power in multiplication. We do this until the first time we get all the way back to the identity element. The smallest number of times, if you will, that we raise an element to and first get back to the identity is the order of that element. In this case, the order of 1 is 12. When, under the operation, there is an element that generates all of the elements of the group, we say the group is cyclic, and that that element is a generator of the group. Now, let's look at the element 2. 2 plus 2 is 4, plus 2 again is 6, then 8, and 10, and then back to the identity. 2 has an order of 6, and since we did not generate any odd elements, we know that 2 is not a generator of the group. The same scheme can be seen for the element 3. So 3 has an order of 4. For the element 4, 4 has an order of 3. Something interesting happens when we get to the element 5. 5 plus 5 is 10, and then because of modulo addition, 10 plus 5, we go right past the identity and get to 3. But like successive powers, we add another 5 and get to 8, and this continues until we actually do get back to the identity 0. So 5 has an order of 12. It is also a generator of the group, as 12 is the lowest power we raise to and get back to the identity. 6 is easy. 6 plus 6 is the identity, and 6 is its own inverse, so 6 has an order of 2. 7 is an order of 12 and generates the group. 8 has an order of 3. 9 gives us 9, 6, 3, and then 0. 9 has an order of 4. The element 10 has an order of 6. 11 also generates the group. As successfully you can see that we have just a countdown, so 11 has an order of 12 and generates the group. Hopefully you've made some notes on which elements generated the entire group. The element 1, the element 5, the element 7, and finally the element 11. The interesting thing here is 1 is the basic building block, the unit number if you will, and all of the other numbers are prime numbers. But what happened to 2 and 3? Well, you can see that both of these actually divide the order of the group. They are not relative prime to the order of the group. Comparing the order of element to the order of the group helps us understand the structure of the group, and so for our additive group of integers modulo 12, the elements and their orders, 0, the identity element, by definition, has an order of 1. Notice the order of the other elements is always a factor of 12. 1, 2, 3, 4, 6, and 12. If the order of an element is the lowest power we raise or number of times we perform an operation to get to the identity, a raised to the k equals e, then raising an element to any multiple of that order will continue to give the identity. 2 raised to the 12 is just 2 raised to the 6 twice. So 2 raised to the 6, 12, 18, 24, and so on is still the identity. This rule holds for every element. Any element a raised to the power k is the identity if and only if the order of a divides k. Because of this theorem, we can see that the order of any element must be a factor or divide the order of a group. But this is an if and only if statement, and we only ever even get back to the identity for certain groups. Remember our group of integers? If we raise 1 to any number, we'll never get back to the identity, so be careful. An element does not always have a finite order. One final thing, and we can see this for every element in our group, but we will focus on the order of 4, which was 3, 0, 4, and 8. These were the 3 points we used for our group D6, and the motions of symmetry of the equilateral triangle. Closed binary operation, associative, identity element, and every element has an inverse. For this, we say the set, which we will call H0, 4, and 8, is a subgroup of our group G, 0 through 11. We will explore more about subgroups in our next video. And don't forget to like down below, and please help the Group Garage channel grow by subscribing and telling a friend.